Hello everyone, my name is Nathalie Rauschmeier. I'm working as an applied scientist at AWS. Welcome to my webinar. Today you are going to learn how to train and tune your models with Amazon SageMaker. First, a brief overview about the content of the webinar. In the first part, I will give an introduction into SageMaker Debugger and SageMaker Experiments. These are two very new features in SageMaker. And in the second part of the webinar, I will give a live demo where I will show you how you can use SageMaker Debugger and Experiments to perform iterative model pruning on SageMaker. First, a high-level overview of SageMaker. SageMaker is our fully managed machine learning service that allows users to more easily build, train, and deploy machine learning models. When we think about machine learning, then it's not just about creating and training a model, but there are a lot of different steps involved. One of the most important steps is to create high-quality training datasets. SageMaker provides a feature called ground truth that allows you to more easily and more quickly generate good training datasets. You can create labeling tasks that you can outsource to people within your organization or to Mechanical Turk. Once you have good training data available, it's time to build and train a model. SageMaker provides a lot of new features here. SageMaker Studio is our fully integrated development environment for machine learning. It comes with a lot of different tools that you need for machine learning development. SageMaker Debugger is another feature that we will focus on today in the webinar. Debugger allows you to emit tensors from your training job and to identify training issues. Autopilot is another feature that automatically trains and tunes the best machine learning model for your classification or regression task. When you do machine learning, then this requires a lot of machine learning expertise. You have to prepare features, select algorithms, optimize model parameters, and AutoML, Autopilot, takes care of all the heavy lifting. SageMaker also provides a new notebook experience. SageMaker Notebooks allows you to quickly spin up a machine learning notebook in seconds and to also easily share it with just a single click. And SageMaker provides experiments that allows you to easily visualize your different machine learning experiments and iterations. Once we have trained a model, it's time to tune it. SageMaker provides a feature, Automatic Model Tuner, that does hyperparameter tuning. And hyperparameter tuning is a very important step because it can greatly improve the model performance and model accuracy. Once we have a tuned model, we can use SageMaker Neo to optimize our model for inference on a specific hardware target. And once we have an optimized model, we can either deploy it to the edge with Greengrass or deploy it to the cloud. Once we have a deployed model, it's not over yet. SageMaker recently released another feature, Model Monitor, that allows us to detect shift in data distributions. So when we train a model, we train it on a certain training data set, and once the model is deployed, it may happen that the data the model sees during inference does not match the data distribution it has seen during training. And Model Monitor allows us to automatically detect that. In this webinar, we will focus on the build and train part, and more specifically, we will focus here on debugger and experiments. Let's start first with a high-level overview of SageMaker Experiments. When we do machine learning, then this is quite often an iterative process, which means first we start with creating a baseline model, and then once we have the baseline model, we start modifying hyperparameters. We may modify the model, we add additional layers, we maybe change the pre-processing. So it's a very iterative process, and in the end of the day, it may be sometimes a bit difficult to track all these different iterations. With SageMaker Experiments, we can now easily track all our experiments at scale. We can organize it, we can visualize it in Studio and log all the different metrics. This allows the user to more quickly iterate. So when we think about SageMaker Experiment, we can think of it as some form of folder structure. So let's say I want to create an image classification model. I would then create an experiment called image classification experiment. And now I perform different iterations. And every time I have a new iteration, I would create a new trial within that experiment. As an example, I maybe create a convolutional neural network, CNN with 20 layers, the next time with 30 layers. Then I may introduce a batch norm layer. And each of these iterations is basically a trial. Within the trial, I can have multiple trial components that basically present a step in the trial, which can be, for instance, training, it can be pre-processing. And so you can think of SageMaker experiments in the form of folder structure. That is also how it's then basically presented in SageMaker Studio. So this is the experiment view where you can now select the different trials. You can open them in the trial component list, then see the different parameters of your training job, and then also visualize them to see how do the different jobs compare. Now I would like to focus on SageMaker Debugger, and we will do a deep dive. So SageMaker Debugger is a feature that allows you to automatically emit tensors from your training job. Debugger supports what is called zero code change. That means you do not have to modify your training script at all. You only have to provide a configuration in the SageMaker estimator, and we will see later on how this exactly looks like. Debugger comes with built-in rules. We developed those built-in rules to automatically find training issues in your model training. So when we train deep neural networks, there are certain issues that quite commonly happen, like for instance, vanishing gradient, losses not decreasing. And Debugger has built-in rules that can automatically find those problems. With Debugger, we can also perform real-time monitoring. That means we start our training job that is going to be executed and on a training instance. And while the job is emitting tensors, we can read those tensors into our notebook instance and perform all sorts of visualization, analysis, and so on. Debugger is also integrated in Studio. And you can, for instance, see the built-in rules that are executed. You can see the status of those rules, whether they found an issue or not. So how does the architecture look like? So when we execute a SageMaker training job, then the job will run in a training container. This training job will then emit tensors to Amazon S3. And when the training job runs with built-in rules, they will run in a separate rule container, so they don't interfere with the training job. And you can have now multiple rules executed, and you won't be charged for the execution of those built-in rules. And these built-in rules will read the tensors from Amazon S3 and check for certain training issues. They will emit metrics to CloudWatch, also to the SageMaker notebook, and you can also see the status of the rules in SageMaker Studio. So let's have a closer look how we can emit the tensors. When you perform SageMaker training, then typically you have to define an estimator object. So an estimator it's a higher level API in SageMaker used to define the SageMaker training job. We have to indicate here our training script. So in this case, I'm training a TensorFlow model. It's an image classification model, and the definition is an mnist.py. I also have to indicate an execution role because SageMaker will spin up a training instance. And here I indicate the instance type where the training is going to happen. The only thing I have to provide now in order to emit tensors is this debugger hook configuration. SageMaker Debugger comes with default collections. A collection is a set of tensors like weights, gradients, biases. But I can also very easily create my own custom collection. Later on in the demo, we will see how we can do that. So for instance, when I want to not just have the weights and the biases, but maybe also the activation outputs, I can easily create my own custom collection here. And we will see later more in detail. So now let's have a closer look on the automatic error detection. SageMaker Debugger comes with 18 built-in rules. We have rules specific for deep learning applications, but also more generic for machine learning applications like XGBoost. So the built-in rules we provide is, for instance, vanishing and exploding gradients. So this is an issue that quite commonly happens when you train deep neural networks. So here's an animation of a model that I trained, and then I retrieved the gradients from the model with SageMaker Debugger, and I plotted the distribution of gradients as training progressed. What we can basically see is the order of gradients here is very small. It's in the order of power to -8, -9. It even becomes smaller as the training progresses. And that's a typical problem of vanishing gradient. This may either indicate that your model converged, or if you see that from the beginning of your training job, it's an indication that something is wrong in your model, that maybe you need to change your hyperparameters. We also have built-in rules that check activation functions. When we create a deep neural network, we may have activation functions like tanh or sigmoid or relu, and these are activations that can saturate. Saturation basically means these activations will only produce small gradients. And let's have a look on the relu activation. The relu activation stands for rectified linear unit. That means for negative input, it will output 0, and for positive input, it will output positive values. There is a problem that is called the dying relu problem. And what this refers to is that if all your for every single training batch in your training loop, if all of that is negative, basically the relu will only output 0 and its gradients become 0 too. And that means the layer basically does not learn well anymore because the activation only outputs 0. And we have a built-in rule that basically can measure how many of your activations suffer, or how many neurons suffer the dying relu problem. We also have a built-in rule that measures the weight updates, so whether your weights between different iterations get updated a lot or maybe not updated at all. We also have some more generic rules that you can use for deep learning, but also XGBoost models. So we have rules that check, for instance, if the loss is decreasing or not. So let's have a look. When we train a model, then we get typically the train and the validation loss. What we may see is that the training loss is going down, but the validation loss is not converging at all. And that is typically a problem that your model is overfitting. That means your model is performing very well on the data it sees during training, but not well at all on the data it has never seen. So it basically does not generalize. Another problem that can occur is, for instance, your training loss and validation loss goes down, but at some point in time, your validation loss goes up. And that happens when your model is training for too long time. It's basically overtraining, and you should apply early stopping. And SageMaker Debugger provides built-in rules that can basically find these issues and then notify you about that. We also have built-in rules that measure, for instance, class imbalance. So let's assume you're training an image classification model, and some classes in your training data set may have less examples than other classes, and it may happen that your model now predicts well the classes with a lot of examples, but not so well the classes that have only few samples. And we have a built-in rule that can automatically measure the mispredictions of your model per class. Then we also have a built-in rule that measures, for instance, the variance of your tensor values or whether the tensors change a lot across different steps. So let's have a look how we can run those rules. Going back to the estimator object, where we define this TensorFlow estimator, we have here the debugger hook configuration. And in order to run the built-in rules, what you need to provide is a list of rules you want to have executed. We use here the SageMaker Python SDK. We use here rule and rule configs to basically get here the vanishing gradient and the loss is not decreasing rule. And they are added to a list. And this list is now passed into the estimator object. So what will happen is if you start the training will happen in the training container, and SageMaker will automatically spin up a rule container where now the vanishing gradient and the loss is not decreasing rule will be executed. SageMaker Debugger also allows us to write our own custom rule. What you have to do is you have to provide a class definition that inherits from the rule base class in SMDebug. And the function you have to define is invoke at step. Invoke and step will be called every time tensors of a new step are available. And the step is basically one forward and backward path. What you have to do is you can now retrieve the tensor names. That happens here, tensor names, and you basically access here the base trial object. The base trial is an object that basically allows you to access the tensors in Amazon S3. Here we are just interested in the gradients. And then in order to access now the values of this tensor, we call now base trial.tensor. We pass in the tensor name. And then we have here a NumPy array available where we can now just perform some computation on it. And in this specific rule, I'm basically just checking if the value 42 is in my tensor. If so, I return true. That basically means I found an issue. Otherwise, I return false. And we also have a lot of examples for SageMaker Debugger in our official example repository in SageMaker. So I put here the link, and there is one example specific for how to run a custom rule in Keras. So please feel free to check that out. So we can now connect the rule with an action. And that's actually a powerful feature, because if our training job runs into a certain issue, it might be worthwhile to stop the training job and not continue training a model that will actually result in a low quality model. So how can we do that? Our training job will emit the tensors to Amazon S3, and the rule is executed in the rule container where it's reading the tensors from Amazon S3, and it will either return false or true. If it found an issue, it will return true, and everything goes to CloudWatch. So we can now set up a CloudWatch alarm and connect that to a Lambda function that will automatically stop our training job. And we will see later on in the demo how we can do that. So let's have a look on the real-time monitoring. So when your training job is running and emitting tensors, you can go to your notebook instance and do all sorts of analysis. The tensors are available in form of NumPy arrays. That means you can use tools like NumPy, SciPy, Scikit to do different kind of analysis and visualization. So we can, for instance, plot the distribution of weights as the training progresses. So we can see how they get updated. We can, for instance, plot the distribution of activation outputs. So I did that for my Relo activation here, and I can, for instance, see that as the training progresses, more and more outputs are actually 0. I can also plot the distribution of gradients, and in this example, see that I'm running into a vanishing gradient issue. And I put here 2 more links for examples in the repository where we do the real-time monitoring with distribution of gradients and weights. So while we talk to customers, we also see that depending on which kind of model you are training, whether this is a computer vision model or whether this is a natural language processing model, you might be interested in different sorts of real-time monitoring and different sorts of analysis. So for instance, what we can do with Debugger is we can retrieve specific tensors and compute in real-time TSNE embeddings. TSNE is the stochastic neighbor embeddings. What TSNE does is it takes our feature vector, which presents a highly dimensional feature space, and maps it into a 2- or 3-dimensional space where we can nicely visualize it. And what the animation here shows is I retrieved here the bottleneck layer of an autoencoder model that I trained on MNIST. And MNIST is a dataset that consists of 10 image classes. And I computed here the TSNE embeddings and visualized it in real time. And what I could basically see is that in the beginning, the model would not be able to separate these different image classes here. But as the training progressed, it became better and better. So that indicated that the model learned meaningful features to separate between these different image classes. What we can also do is we can, for instance, monitor class activation maps in real time as our training is ongoing. Class activation map it allows you to create a heat map like the following. So what does the heat map tell us? This is an image classification model that I trained on a German traffic sign dataset. And the heat map basically tells me where is the CNN looking at when it's making a prediction. I have here in the title the predicted class with the probability. And red basically indicates me that the model is looking here into the center where the traffic sign is. But what we see in the beginning is that the model focuses basically on the lower left obstacle in the very beginning of the training because it has never seen a traffic sign before. And so because of that, it's doing in the beginning some mispredictions. And what you do in this class activation maps, you basically have a prediction vector. And you go then backwards into the model to identify the neurons that fire the most to make this certain prediction. And what you have to get here is the gradients and the activation outputs. And with Debugger, you can automatically and easily retrieve those tensors. And then you can create a heat map to understand, okay, which kind of features is my model actually picking up when it's training? And if it does a misprediction, why is it actually happening? If you're training a natural language processing model, then you might be interested, if you are training a transformer model like BERT, you might be interested in the attention scores. What we see here, this is now, I trained here a BERT model on a question answering dataset. So we see here the different input tokens into the model. And we can now basically select different steps, different heads and different layers of the model to see which tokens have high attentions to other tokens. So the thicker the line here, the higher the attention. And we can plot that across different steps to simply identify, okay, which kind of semantic meanings is the model learning in the different heads and in the different layers. And we have, again, here a link, so please feel free to check that notebook out. So now I would like to focus on the demo. So in the demo, I will show you how we can use now Debugger and experiments for a specific use case. I will show you iterative model pruning. And first, why should we actually care about model pruning? So model pruning is a technique that basically allows us to reduce the number of parameters in our model, which results in a smaller model size, in faster training and faster inference. So first, a brief introduction into model pruning before we jump into the notebook. So I put here a diagram that shows some of the state-of-the-art models from the last years that achieved state-of-the-art results on ILSVRC, which is the ImageNet Classification Challenge. And deep learning models became better and better in image classification. And nowadays, models like ResNet or ResNext actually achieve better performance than human beings in image classification. When we look at the number of parameters of these models, then we see that they vary a lot. AlexNet, for instance, has around 62 million parameters. VGG has around 138 million. But the number of parameters does not necessarily tell me whether the model will perform well or not, because a model like GoogleNet has only 7 million parameters and achieved state-of-the-art in the year 2014. And these models are typically trained on very large data sets, and training them from scratch may take a lot of time. But typically, data scientists perform transfer learning, where they take a pre-trained model and train it now on a smaller data set. So it may not always be necessary to have that large amount of parameters in the model. With SageMaker Debugger, we can actually even visualize our tensors in 3D. And that's an example visualization that I created. This is a small image classification model that consists here of several convolutional layers. This is the input into the model, and these are the fully connected layers. And here we have the predicted output of the model. So what does this visualization tell me? What we can see is a lot of areas are actually blue. So the color basically means if it's blue, the neurons are not active much. But if I have red or yellow, that basically means the neuron fired a lot. And I can see now that there is a large part in my model that actually never really fires throughout the whole training. And that tells me that I could prune that model and have a much smaller model for the given training data. And there are different techniques to prune a model. One is non-structured weight pruning. What we do here is, let's imagine we have a model with a couple of fully connected layers. After training, there are now some weights that are very strong and other weights that are only small. And we can now remove the low weights, so we have less connections. Another technique, which is specifically interesting for computer vision models, is structured pruning. In structured pruning, we remove entire filters and channels in convolutions. Let's have a quick look what's happening in a convolution. So let's assume we have an input image like here that only has one input channel because it's a black and white image. And a convolution has now a filter. A filter is a set of kernels which will produce a feature map. And typically in a convolution, you do not just have one filter, but you have multiple. So in this case, for instance, 3. The number of parameters the model is going to learn is the number of input channels, multiply the kernel width, multiply the kernel height. In this case, we have 3 of them. And typically, you're not just having 3 filters, but maybe a whole block of filters. And what we can do in structured pruning is we identify the filter that has the smallest value. So let's assume the yellow filter is the one that is the smallest one. We can just prune that filter. That means we reduce the number of parameters now by kernel width multiplied kernel height. So we have less feature maps. There are different techniques to filter, to rank the filters. So one is, for instance, you can just take the minimum weight or the average activation. And what I'm going to show in the notebook is I'm using the same method as it's described in the paper here, pruning convolutional neural networks for resource efficient inference. What they do is they take the product of the activation output and its gradient of the cost function with respect to the activation output. I don't want to go too deep into detail, but that's basically the method I'm using to rank the filters in the notebook later on. So let's have a brief look on how we can facilitate model pruning on SageMaker. So when we go to the SageMaker notebook instance, we basically create now a training job. And I'm using now SageMaker Experiments to create a model pruning experiment. And each training job within that experiment will be one trial. The training job is now emitting the weights, gradients, biases to Amazon S3. And I can now read them into my notebook instance and compute filter ranks. Once I know which filters have a small rank, I can prune them. I create a new model definitions with the pruned weights, and I can start the next job, which is a new trial in the same experiment. And I can now iteratively perform that several times. And then in each iteration, I will get a smaller and smaller model. And I have added here the link to the example notebook. Okay, so let's have a look at the demo. So this is SageMaker Studio. We see here the different notebooks and different files. And this here is the SageMaker experiment view where we can see the different experiments that were executed and also the different trials in an experiment. But let's start with the notebook. So what I'm going to do in this notebook is first, I will load and save a ResNet model. I will take the model from the PyTorch model zoo, and I take it with pre-trained weights. It's a ResNet 18 model. And how the model looks like, so ResNet consists of a lot of basic blocks. Each basic block has 2 convolutional layers followed by batch norm and relo activation. And there are residual connections in ResNet that basically allow the input to bypass the basic blocks. I'm training this ResNet 18 model on the callback dataset, callback 101. That means the model is now only outputting 101 classes. So ResNet 18 is pre-trained on ImageNet, which has 1000 classes. So the first thing I have to do is I have to take the last layer of my ResNet model and modify it to only output 101 classes. In the next step, I'm going to save the model with the pre-trained weights in a checkpoint file, and I store this file under the source directory. The source directory is the directory where also my training script is located. So when I start my training job later on, SageMaker will pick up the training script from there and also the latest model file. Once I have done that, I create a SageMaker experiment, and that's what's happening here. In order to do so, I use the Python library SM Experiments. It's open source, so you can just do a pip install SM Experiments. And in order to create an experiment, I call this function here. I have to indicate now a name. So in my case, I'm creating a model pruning experiment, and I add a time tag so that later on I can more easily distinguish between the different experiments. And once I have created that experiment, now it's time to I create next a trial. So when I perform the model pruning, each job will be a new trial in the experiment. And in order to create a new trial, I call now the function trial create, where I indicate the experiment to which this trial belongs to. And later on, in order for SageMaker to be able to associate my training job with a specific experiment and a trial, I have to pass in an experiment configuration, and that's what I'm defining here. It's a dictionary where I set the experiment name and the name of the trial, and it will be passed to SageMaker later on when I start the training. In order to compute filter ranks, I need to have gradients and activation outputs. And as I said in my presentation, SageMaker Debugger provides default collections for weights and biases, but in this example, I'm also interested in the activation outputs. So I create now a custom collection. What I have to do is, in this custom collection, I indicate now a regular expression of the tensor names that should be included in this collection. So in my case, I'm interested in the RELO activation outputs, in the weights, the biases, and also because ResNet has batch norm layers, I'm also interested in the running mean and the running variance of those batch norms. I set the default interval to 100, so tensors will be saved every 100 steps. One step means one forward plus backward pass. Once I've defined that, I'm ready to start a training job. I'm defining now my PyTorch estimator, and I pass in the debugger hook configuration so that the training job will start emitting my custom collection here. Now I started training. This is happening here, estimator.fit. And as I said before, for SageMaker to be able to associate my training with an experiment and a trial, I have to pass in now the experiment configuration. So once the job is training, the tensors will be emitted. And now I can start reading those tensors. In order to do that, I use here the SMDebug library. SMDebug is open source. You can just do pip install SMDebug. And it comes with all the functionalities and utilities we need to read and filter tensors. It provides a function called create trial. And for clarification, in the context of SageMaker Debugger, a trial is an object that lets you query tensors, while in the context of SageMaker Experiment, a trial is a part of an experiment. And create trial in debugger, in SMDebug, allows us to create a trial object with which we can access the tensors. What we have to do is now we pass in the path to Amazon S3 where the tensors are located. So we just access the estimator object and call latest job debugger artifacts path. And that's basically the S3 path we get. And I pass it into the create trial function. Once I have the trial object, I'm able to access the tensor values. So now I'm ready to compute filter ranks. And that's what I'm doing in this part. I'm iterating now over the different steps in my training. So I'm accessing here smdebug trial.steps. So all the different steps that have been recorded by debugger and for which tensors are available. And in order to get the tensors, I'm now calling smdebugtrial.tensor. Then I pass in the tensor name, and let's have a quick look. The names are defined here. Here I define the list of names that I want to have pruned. And then I pass in this name, and then .value step gives me the tensor value for the corresponding training step. And I do the same for the gradients. And in order to compute a filter rank, what I have to do is I compute now the product of my activation outputs and gradient and compute the average over the filters. And I do that for all the steps that are available. Now I do some further computation where I normalize the filters and then I sort the filters by size. That's happening in this part. So once I have sorted filters, in this case, I'm getting the 200 smallest filters. I basically have a long list. And so what does the list tell me? Let's have a look on the first element. So this entry tells me that I can remove the 261st entry, 261st filter in my fourth layer, because it has a very small rank of 6.4 to the power of -6. And so I have now this list that I pass into a function. So I defined now a pruning function. It's in the script here. And what I'm doing there is I'm basically iterating now through all the different layers of my model. And then I check if the current layer is a convolutional layer or not. If it's a convolutional layer, I check in this part if my current layer is a layer that is supposed to be pruned. If this is the case, what I will do is I will take the weights, and now I just call num_by_delete, where I pass in the filter to be removed. And then I also set a new output channel, which is happening here. So if I remove filters, I will create less feature maps. Then I'm taking here the weights, the pruned weights for my last training job, and set them now in the layer. And in ResNet, there are batch norm layers. So here I have to do the same for the subsequent batch norm layers, where I also have to remove the weights at the corresponding, have to prune the weights as well. And that's basically happening in this script here. And so once this function is executed, it basically will output me some results. It tells me now that my first layer, that the filters have been reduced from 64 to 61. Then in the next layer, it has been reduced from 64 to 62, and so on. And then when this is done, I have a new model definition, and I have pruned weights, and I saved that in a new checkpoint file. So when I start another training job, it will now pick up the latest weights and the new model definition. And what I'm doing here now, this basically here I put all the pieces that I just explained together in one giant loop. I basically run 10 pruning iterations, and each iteration I'm creating a new trial. Then I execute, I define this estimator, then I execute the training, compute the filter ranks, prune the model, and then save the model definition. And now I'm basically executing that 10 times. So once the model pruning experiment is running, we can go to the SageMaker experiment view. And we can now select the different trials that have been executed, and we can visualize the different trials. So let's have a look here. What we see now is here the validation accuracy, and we have here the number of parameters. So we see that my first training job started with 11 million parameters, and after 10 pruning iterations, I had only 706,000 parameters left. And when we look at the validation accuracy, we see that the model was roughly at 90% accuracy, but then at some point in time, it started dropping. We can now also create a visualization with SageMaker Studio. Here I'm using the summary statistics and then scatter plot. And then I plot the number of parameters versus the validation accuracy. And we can see now that I can drastically reduce the number of parameters in my model without actually sacrificing the accuracy too much. But there's a certain point in time when accuracy will drop quite a bit. And what we can do now is we can use SageMaker Debugger and define a custom rule that will identify when my accuracy is dropping too much and then stop the training job. And that's what I would like to show now. So here I'm doing the same like before. I'm running the iterative model pruning, 10 iterations, but this time I'm executing my training job with a custom rule. So in this custom rule, let's have a look on the code. In the custom rule, I inherit from the rule class, and I basically implement this class here. Then the function invoke and step is defined where I'm basically in each iteration compute the accuracy of my current training job. And the rule takes now the input into the loss function, which are the predictions and the labels, and it takes the accuracy of the previous training job. And then I just compute my current accuracy and compare it against the accuracy of the previous training job. And if it drops by too much, I just return true. And I can now create a CloudWatch alarm that I connect to a Lambda function. So whenever this rule returns true, I stop the training job and I exit the experiment. So in order to run this custom rule, what I have to do is I have to provide a rule configuration, and that's happening here. I have to indicate now an image URI because when the rule is running, it will run on a different instance, in this case a C4 instance, and it will run in the rule container. And so I have to provide here the image URI for this rule container. And you can check out the documentation where you can find a corresponding URI for your region. So in this case, this is the URI for US East 2. Next, I define where the custom rule is located. So I stored it here under the source directory. That is where this file here is located. And then I can also define the parameters the rule is taking. So in my case, it takes the accuracy of the previous training job. And then my loop looks like the following. When I define now my estimator, I have to pass in here my custom rule. And now I have to, once the training job has finished, I have to get the accuracy of my last training job to update the rule configuration. And that is what's happening here. I use the experiment analytics module. You can use it from here, SageMaker Analytics, import experiment analytics, and I pass in the experiment name. And I can now convert that into a data frame where via that key here, I can now retrieve the accuracy values of all the training jobs from this experiment. And with taking the first entry is basically the accuracy value of my last training job. And so once I have this value, I pass it into my rule configuration so that my next job that is going to be executed, the rule knows then what was the accuracy of the last job. And since I have now a CloudWatch alarm and a Lambda function that will stop the training job if the rule returns true, I basically check here now if my last training job has been stopped, because if this is the case, I exit the loop and I'm not going to execute any more training jobs. And we can have a look on how this looks like. I go now to the experiment that I have been running with the custom rule. And we see now that my last training job has been stopped, so it has not completed. And basically, that was the point in time when my accuracy would have dropped quite a bit. And we can now also open that in the trial details. And when we go to debugger, we see now that in my last training job, the rule found an issue. And we can, of course, now also create a much more complex rule. So in this case, I just was interested in the accuracy. So basically what happens if you prune too many parameters, your model has a low capacity and it may not learn meaningful features anymore. So accuracy drops. and we may want to avoid the situation. And we can now even create more complex custom rules where maybe we say, okay, we want our model to have at least a size of only 100 megabytes, at least an accuracy of 90%, and then put that into a custom rule. So whenever this condition is met, I stop the experiment and I'm not producing more training jobs. And the same I have shown right now, I repeated the same experiment also for a different model, AlexNet. And let's just have a quick look how the experiment looked like. I see here now that my experiment started with 58 million parameters, and then after about 12 pruning iterations, only 8 million parameters are left. And the accuracy here started slightly slower, and we see that it then drops quite a bit. And so here's a visualization of that example. So it's, of course, a different model. So pruning here has, depending on the model, a different impact. So we have seen now in the demo how we can do the iterative model pruning on SageMaker. And I created here also a visualization of, this is now for AlexNet, of what is happening during the pruning, so which layers get pruned the most. What we see here in the animation is, here's the pruning iteration. Here we have the number of parameters. So my model started with 58 million parameters and then went down to about 18 million parameters. And then here we also see the size of the model. It started with about 220 megabyte. And then after 10 pruning iterations, it's about 70 megabyte large. And we can see now which layers get pruned more. So typically you would see that the last convolutional layers get pruned more than the initial layers, because the initial layers learn some more important features in your training data. So in this webinar, you have learned how to use SageMaker Debugger to get insights into the model training, and how to use experiments to keep track of your experiments and the trials. And in the demo, you have seen how you can use Debugger to compute filter ranks, and how to write a custom rule to stop the training. And we have used SageMaker Experiments to keep track of the different pruning iterations. I hope you enjoyed the webinar. If you want to learn more about SageMaker or machine learning on AWS, I would like to share a few resources with you. At Amazon, we want to put machine learning in the hands of every developer. So we've expanded the machine learning curriculum we used to train thousands of Amazon's own developers and made it available digitally for free. There are more than 65 on-demand courses available on a range of topics. We also offer role-based learning paths specific for developers and data scientists, so that you can focus on the content that matters most for your role. If you prefer a classroom setting, we also offer live classes with accredited AWS instructors who teach using a mix of presentations, discussion, and hands-on labs. These are offered all over the world, and we constantly develop new content. We also offer many different training options specific to SageMaker, and I encourage you to visit our learning library to check them all out. On this slide, I want to highlight 2 of them, but there are many more available, of course. In Amazon SageMaker, build an object detection model using images labeled with ground truths. You learn how to implement a machine learning pipeline using SageMaker and SageMaker ground truths. You will use ground truths to create a labeled dataset and then train your own object detection model. Another brief digital course is automatic model tuning in Amazon SageMaker. In this course, you learn more about SageMaker Automatic Model Tuner, a feature that you can use to optimize the hyperparameters of your model. And the final link on this slide will take you to a machine learning filtered view of our learning library, so you can check out all the courses we offer on machine learning, including digital courses, classroom courses, individual instructor-led courses. And one final resource I would like to mention is our newly developed machine learning ramp-up guide. This guide offers recommended resources like videos, white papers, technical guides, and many more. Thanks a lot for attending my webinar.